Welcome to our first proper lecture for Math 311. We're going to be meeting online, as you know, for the next few weeks. So, because I don't trust my internet connection, I want to do the actual lectures online, or recorded, and then we'll do sort of work sessions together over the next few days. Presumably on Wednesday is the best day to do it. And I plan to just schedule 3 consecutive hours for me to be available, and you can sign up for one of the slots so that it's groups of 10 people working together. So you can expect another doodle poll on later today to sign up for slots on Wednesday. Okay, so before the break, we started talking about modular arithmetic. And what modular arithmetic does is it creates a new set of numbers to work with. I mean, they're built from our usual integers that we can add, subtract, and multiply, but there's much fewer of them. There's only finitely many. So in modular arithmetic, or in arithmetic mod n, there are only n numbers. And they're represented by 0, 1, all the way up to n, minus 1. And the reason we do this is because each of these represents an equivalence class. So really when I write 1, when I work in arithmetic mod n, I mean 1 sub n, which is the equivalence class of 1 modulo n, which are all the things equivalent to 1 mod n, which turns out to be 1 plus a times n, where a is any integer. So this is our equivalence class. Let me just remind you of what the equivalence relation is. We say that a and b are equivalent mod n. If and only if n divides a minus b. And we proved that this was an equivalence relation and that there were n equivalence classes and things like this. So what were the things that we proved we could do with modular arithmetic? Well, we proved that we had addition mod n. We had multiplication. Mod n. We had subtraction. And we can just define subtraction as adding minus something. So in a way, having subtraction well-defined mod n is saying that it makes sense to take minus a number. So if I have minus 2, so for instance, if I considered things mod 5, if I wanted to look at what the opposite of 2 was, modulo 5, this is the same thing as 3, mod 5. When I take mod 5, it means that I can add any multiple of 5 to my number and still stay in the same congruence class. So if I start from minus 2 and I add 5, I get to 3, and 3 is the unique representative between 0 and 5, not including 5. So it's usually ideal to express numbers this way, even though you can choose any integer in the equivalence class to represent the number in the congruence class. So in this sense, subtraction makes sense, and so does taking opposites. But the opposite of division, what's the opposite of, the opposite of multiplication? What's that? It's division. And division doesn't always make sense. Division makes sense sometimes. And this is one of the biggest sort of hurdles you have to overcome when you want to work in modular arithmetic. And to be honest, it's kind of a miracle that you can divide at all, because if you think about the integers, to be able to define division, the only things you can divide by are 1 and -1, right? Those two numbers. Everything else doesn't have a well-defined division unless there's a very specific relation between the two numbers you're looking at, right? You need to, for b divisible by a, well, we define that relation, right? We'd have a divides b. So division here will make sense sometimes, just like usual, but it will make sense more often. So let's see what we mean by that. So last time, actually, I wrote down the number, but I didn't write down the theorem. Let me make sure that I write it down as it's written in the book. Last time we proved corollary 1.4.4, and I am going to start using the book's numbering more carefully. And what does this corollary say? It says, if A times C is congruent to B times C modulo n, then and the GCD of n and c is equal to 1. So the thing that I'm trying to divide by, right? If this was just a usual equation and I wanted to get a equals b, I would divide by c. So to be able to divide by c, I need this condition that c is coprime with the modulus. So if c is coprime with the modulus, then I can actually divide. And this is basically an if and only if condition. It's not exactly an if and only if condition, because you'll be able to, and we'll talk about that soon. If it's not coprime, they may be equivalent, but you get some lower order of equivalence. They may be, they're only guaranteed to be congruent in some lower way. So I just write this to recall what we did at the end of class before the break. And you can look at the book. It's basically just a string of inequalities, or a string of equalities that uses the fact that this condition is equivalent to being invertible. And that's the other main theorem we proved. And that was theorem 1.4.4. So proof, I'm out of paper here. So this proof uses theorem 1.4.3. So I encourage you to look at that, and if you're confused about it, we can talk about it in one of these work sessions. And if people are still really confused about it, please let me know, and I will write up or post another video with the proof of these two things. So this is sort of the best case scenario, when things are invertible and you have this GCD condition. So let's discuss what happens when you don't have this GCD condition. And this leads us to our next definition. A is called a zero divisor. Mod n. If there exists B in Zn, so there you can find another element, another congruence class, such that A the congruence class of A mod n times the congruence class of B mod n is the congruence class of 0 mod n. And B, this congruence class is not equal to 0. So being a zero divisor is a big problem, right? Because you should never be able to multiply one number times another number and get 0. At least this breaks most of our intuitions. I mean, a lot of things in modular arithmetic break our intuition, but this in particular turns out to be something that causes big problems. So here's our next corollary. I don't know why it's called a corollary. So this is corollary 1.4.5. So every element of Zn, remember elements of Zn are congruence classes. And here I should really say B is an element of Z, because I'm taking the congruence class of B. So that's not a great, but this definition still works. So every element of Zn is either a zero divisor or invertible. Okay, so the non-invertible elements are zero divisors, and the zero divisors are never invertible. You can never get to 1 if you can get to 0, and you can never get to 0 if you can get to 1. So yeah, this is a corollary of theorem 1.4.3, which says that an element is invertible if and only if the GCD with n, where n is my modulus, is equal to 1. So what do I know? So proof. It'll be good to do it on one page anyway. So proof. First, suppose it will start out the same. A is not invertible. Again, by theorem 1.4.3, the GCD of A and n is strictly bigger than 1. We'll still let D be the GCD of A and n. Now I don't even need the GCD theorem. Then D divides A and D divides n. So n is equal to D times something. A, because D divides n, and A, sorry, so I need a new letter, B, K, let's use K. Right. Okay, so I have this set up, and now what do? I multiply both sides of this equation by K. So it's K times D times L. But K and D can be grouped together. And I know that K times D is just N. But that means that K times A is congruent to 0 mod N. Because any multiple of N represents the 0 class in N. So k times a is congruent to 0, and the equivalence class of a, k times the equivalence class of a, is just the equivalence class of 0. And this means that k is not k is a zero divisor, or a is a zero divisor. Both k and a are zero divisors, in fact. And I forgot one more thing, actually, as well, in my definition of zero divisors. Of course, oh, never mind. It's fine. So this is part of the proof of the theorem. What else do I need to do? I also need to prove that you can't both be a zero divisor and invertible. We don't want any overlap between these two sets. So we'll do this by contradiction. So we'll prove that a number cannot be both a zero divisor and invertible by contradiction. So how does this go? How does proof by contradiction go? You assume the thing you want to prove is wrong, and then you find something wrong with the universe. So what I want to prove is that no number can be both a zero divisor and invertible. So what I assume is that there exists some number that's both a zero divisor and invertible, and get some sort of problems. So suppose that A is both a zero divisor and invertible modulo n. So what happens if they're both, we have both of these things? Well, we need to unpack the definitions. So since A is a zero divisor, I can find some B which is not in the zero class mod n, such that A times B is congruent to 0 mod n. Which is just to say that n divides A times B. Now, since A is invertible, what does this mean? This means that the GCD of n and A is equal to 1. Is this something we showed, or did we use this? We didn't use this, so I can't quite... This is not too difficult to prove. That if A is invertible, its GCD is equal to 1. You just take the equation. So here's a proof of this. Let's do it over here on the side. If A is invertible, there exists B such that AB is congruent to 1 mod n. But then if I unpack this, this means that A times B plus 1 is equal to n times k for some k. And rearranging this, I get AB plus n times minus k is equal to minus 1, or If I put minus signs in front of everything, I get 1 over here. Right, so this becomes a plus, and this becomes a minus, whatever. The point is that I can find some multiple of A and some multiple of N that gives me 1, and that means that the GCD is equal to 1. And this is all I need for this proof here. So invertibility is equivalent to GCD equals 1. So what happens if the GCD is equal to 1 and I have this divisibility condition? Well, we showed earlier that if I have this divisibility condition and the GCD of N and A is 1, then N actually has to also divide B. You can see this from the prime factorization theorem quite easily. If the GCD of N and A is equal to 1, then they don't. When I take the prime factors of N and I take the prime factors of A, they don't have anything in common. All the primes here don't appear here, so they have to appear in B. That means that N has to divide B. But I need that B is not part of the equivalence class of 0 mod N. And this condition is exactly the condition that B is part of this equivalence class. So this is a contradiction. And that ends our proof. Every element is either invertible or it's a zero divisor, and it can't be both. And it's exactly detecting whether or not the GCD is equal to 1. So the GCD turns out to be a very, very important number related to two numbers. Okay, sorry for getting lost and having to rewrite this proof a few times, but I hope it's clear now. Let's do one more theorem from section 1.4 and then we'll move on to section 1.5. So I'll state it here and then we'll prove it on the next page. So theorem 1.4.7 says, and the book writes it slightly differently than I'm going to, but I think that this is the easier way to write it. So if A and B are both invertible modulo N, so is A times B. And there are a number of ways to prove this. I'm going to give my proof here, which I think is the shortest. So if A and B are invertible, then they have inverses. There exists C and D such that C times D is congruent to 1 mod N. And, C times A is congruent to 1. And B times D is congruent to 1 mod N. So what does this mean? This means that if I multiply all four together, just by commutativity of multiplication and well-definedness of multiplication mod N, I get C times D times AB is congruent to 1 mod N. And this is just exactly the condition that A times B is invertible. So the inverse of AB is the inverse of A times the inverse of B, which is just like saying that this proof is just saying that 1 over A times 1 over B is equal to 1 over A times B. Because these two things are well defined, this thing is well defined. That's the structure of the proof. Again, we don't like this notation, but the structure of the proof comes from this equality, the way that we multiply inverses. You can also prove this with the condition that the GCD is equal to 1. So I'll just say it out, and maybe I'll include this as a homework problem. What does it mean that our assumption is that A and B are invertible mod n? This means that the GCD of A and n is equal to 1, and the GCD of B and n is equal to 1. Well, it's not too difficult to see, either from the prime factorization theorem or other methods, that A times B is also has GCD equal to 1 with n. So this theorem is not difficult to prove, but it's very important that when you multiply two numbers that are invertible, it's still invertible. And this will be related, this will come back again later when we talk about groups, because the set of invertible elements will be a group. Okay, so far we've only done elementary school stuff with these numbers, right? We've learned how to add them, subtract them, divide them, and we've proved that all of this stuff is consistent. And now we're finally ready to move on to middle school. And what do you do in middle school? Well, you start solving linear equations. So here's theorem. We're in section 5 now. 1.5 rather, 1.5.1. So fix numbers A, B, and n. And n. So the equation A times x is equal to B mod n. All right, this was a very basic linear equation. If this was just A times x equals B, and you wanted to solve for x, you would divide by A. This is what I was talking about earlier when I said certain equations would have solutions. So A times x is congruent to B mod n. This thing has a solution. If and only if the GCD of A and n divides B. Right, so A here is this number, the thing I'm multiplying x by. It's the multiplicative part of the equation. And n is the modulus. So I need the thing I'm multiplying by, when I take its GCD with the modulus, to be to divide B. Now the solution may not be unique, and the non-uniqueness of the solution is related to how large the GCD is. So there are GCD A n solutions. So if the GCD is equal to 1, there's only one solution, and this is just obtained by multiplying by that inverse, because if this GCD is equal to 1, A has an inverse, so I multiply by A inverse here and A inverse here, and I get that x has to equal that specific number. Now if the GCD is not equal to 1, I can still get solutions, but there are more than one. So there are this many solutions, and they are all congruent modulo n divided by this number. So this is the statement of theorem 1.5.1. It's our basic test as to whether or not we can solve a linear problem. So I'm going to start the proof in this, and then I'll probably finish it next time because we're already at 35 minutes, and like I said, I want to keep these at 40 minutes. So what's the proof? So let's work in one direction. Let's assume this GCD divides B. So I'm going to give it a name. let D be the GCD of A and N, and assume that D divides B. Okay, so now it's useful to break down this equation in terms of, right, we're not only trying to find x, we're going to be trying to find other numbers. We look for numbers x and y such that a times x is equal to b plus n times y. This equation is solved if and only if you can find a y and an x such that this thing is solved. And then x is my solution, y is just some auxiliary thing that's related to the fact that we're taking things modulo n. So now I want to use this condition and plug it in here, right? This is, you have conditions, you want to see how you can use them. So I see that I have that D divides B. I see B appearing here, so I can certainly plug in that condition. So since D divides B, B is equal to, well, let's look at what variables we have. We don't have a K or L, so I'll use a K here. B is equal to D times K for some integer K. Therefore, we look for numbers x and y such that, and I'm going to rearrange the equation. Oops. Sorry, we're looking for these numbers such that, so I start with this equation. Ax minus ny is equal to D times K. And this is where we are. And now I want to use the fact that D is actually the GCD of A and N. I have to use this at some point. Right, I don't know what x and y are. They're my unknowns. That's what I'm looking to try to find. So let me write down that equation up here again. So trying to solve ax minus ny is equal to dk. So now I want to use the fact that D is equal to the GCD. So since D is equal to the GCD of A and N, maybe some of you can already see how this is going to end, I can find numbers, let's just call them x prime and y prime, such that ax prime plus by prime is equal to D. This is by the GCD theorem. But now I just multiply this whole equation by k. A times kx prime minus, oops, this is n, right? It's the GCD of A and N, so it's A times something plus N times something. So it's minus N times, right, I put a minus sign here, so I need to put a minus sign inside as well. K times y prime is equal to K times D. So x equals kx prime and y equals ky prime minus ky prime are the solutions. Okay, so this is the basic step. This is probably the easiest part of the theorem. And next lecture that I post, will prove that these the number of solutions is correct, and that this is really an if and only if. If the GCD does not divide B, then we can't find a solution at all. Okay, so that wraps up the first lecture. I'm sorry that I got lost a few times. It's, you know, just the nature of lecturing that you have your notes, but sometimes you trip up a little bit. So I hope it was clear. I'll do my best to not have too many problems like this in the future. And please let me know if there was any audio-visual problems with the lecture, or if you have any suggestions for formatting or things like that. Stay tuned for announcements regarding our meetings on Wednesday, and I'll see you then. Oh, also homeworks, whatever the number is, the next homework will be posted later today. It will be required to be submitted on Tech, and I'm happy to screen share to show you any tech techniques that you're confused about, or how to set up your LaTeX. The homework will not be long again, because this is, again, only your second tech assignment. So that's all. I hope you're staying healthy, and I will see you on Wednesday. Bye-bye.